Hi, in this video, I'll be going through what is the sub-game Nash equilibrium concept, which I say I would in the previous one. So in the previous one, we checked that Nash equilibrium is not a strong enough concept to explain sequential games, and with that, we need the idea of a sub-game. So a sub-game is an extensive form game where we begin at a decision node that is a singleton information set. It might not be the game's first one, but it has to be a singleton information set. And then it will include all the decision and terminal nodes following that node, but no nodes that do not follow n. And it does not cut away any information sets. So what does it mean intuitively? It's that it is part of the whole game that can become a game on its own. So for example, we just take this example. We got the whole game here. This is a sub-game because you start at this decision node, you got these outcomes. This is also a sub-game. You got start at this decision node, you got this. And this is the whole game already, so it's not counted. So a Nash equilibrium is sub-game perfect if the player's strategy constitutes a Nash equilibrium in every sub-game. And it can be further seen that a finite dynamic game has a sub-game perfect Nash equilibrium in maybe a mixed strategy furthermore. So a Nash equilibrium will rely on non-credible threats, can be eliminated by the requirement of the sub-game perfection. To find the sub-game Nash equilibrium, we start with the smaller sub-games, meaning sub-games that do not contain any proper sub-games. For example, this sub-game contains this as a sub-game, so this is not the smaller. So we start with this, then we move up. So it's something like your backwards induction. You start with the last node, but in this case, we start with the smaller sub-game. And now we consider the second smallest sub-game. And we continue all the way until we have the whole game, which is the beginning. So we start with the first, for example, the entry deterrence. We just start with the smaller sub-game. So player 2 will compare the payoff between L prime and R prime. And notice that L prime is 1 and R prime is 0. So L prime is the optimal strategy for player 2. And after that, you move on to the next node, which is still a sub-game, which is the whole game. And in there now, player 1 compares her payoff function under L and 1 under R. And because she knows that player 2 will choose L prime, we just need to focus on this side. So it is 2 versus 1. And so the SPNE will be L and L prime. Why is it now a difference between, why is the SPNE 2 elements, but when we talk about outcome we only say is 1? So there's a difference, and the difference is a Nash equilibrium must be a strategy profile in the first place. So a sub-game perfect Nash equilibrium must already be a Nash equilibrium, which is a strategy. So the strategy is player 1 chooses L. If player 2 gets chosen, player 2 chooses L prime. So this is the strategy that will be chosen. That's why this is the SPNE. But an outcome is just going to be the path of play, which is going to be the backwards induction outcome, which is just L. So I hope and you see the difference. And if we were to change the payoff function to be different, the backwards induction outcome can be the SPNE, but it need not be the case. In this case, it coincides because in this case, your path of action is first R, then L prime. So the SPNE and backwards induction outcome is the same. So now we just take a look at a more complicated example to further cement our understanding. And in this case, now player 1 has 2 actions, C or E, but player 2 has 3 information sets, here, here, and here. And this game can be now broken down into 3 sub-games. So this 1, 2, and 3. And thus, player 2 can either choose F, G, F, H, J, F, I, J, F, H, K, F, I, K, and so on. So you get the combinations that can be chosen. And under each one, now we just need to work backwards. So if you were to choose from here, you choose this, your indifferent 0, 0, so you can choose F or G. Similarly, H and I is indifferent, so it's 1, 1. But if you take this subgame is J or K, which is 2 or 3, so in that case you definitely choose K. So whenever you choose it, your last outcome, your last strategy will always be a K. You'll never choose J. And so now you can reduce it to 4 combinations, which is F, H, K, F, I, K, G, H, K, G, I, and K. And with that, now we just need to compare. So, after discovering these strategies, we move on to the whole game as we move on to the next sub-game. So in this sub-game now, player 1 has optimal action by choosing, so we just need to see. You just need to look. If player 1 chooses C, then he knows that player 2 is indifferent. So he either gets 3 or 1. If player 1 chooses D, again player 2 is indifferent, so he'll know that he'll either 1 or 2. And if player 1 chooses E, then he'll definitely get 1. So under the combination F, K, H, K, H, K, F, H, K, and F, I, K, player 1's optimal strategy will be to choose C. Because if it's F, H, and K, to choose F, the best strategy is to choose C, because you get 3, 1 versus 1. So I hope you see how to do it. Same for FIK. But now if you have G, H, and K, so it's either you get 1, 1, or 1, then all of them are optimal. So it doesn't really matter. And for the last combination, G, I, and K, your optimal strategy will be D. Because if you got G, I, and K, it's either 1, 2, or 1. So choosing D is the best. And so the strategies will be just paired accordingly. You first have C for these two, and then we have C for this, D for this, E for this, and the last one is D for GIK. And those will be the strategy, the subgame Nash, perfect Nash equilibrium, and the optimal strategies that we need to choose. So I hope it's now clearer with this more complicated example what you need to do for finding the SPNE. I've come to the end of this video. If you have any questions, leave it in the comment sections down below. I would like to hear your thoughts, and I'll catch you in the next one. Bye.